More than 60 years ago, the robot Rosie first appeared on television in The Jetsons. She buzzed from room to room doing housework, seamlessly blending into the Jetson family's daily life. Today, as reality slowly catches up with science fiction, scientists are trying to build a modern version of Rosie. Yet one of the most ordinary household chores has turned out to be one of the hardest challenges of all: folding laundry. What looks like a simple action, picking up a t-shirt and folding it into a neat square, actually requires a deep understanding of how objects move and deform in three-dimensional space. Humans handle this easily because we learn through experience how different fabrics behave when they are folded. Robots, however, struggle to transfer what they have learned to new situations that differ from their training data. As a result, today's robots move slowly and often perform poorly, even on the simplest folding tasks. One major difficulty is that fabrics can be folded in an almost infinite number of ways. Think about how a t-shirt lands differently every time you toss it into a laundry basket. A human can quickly grab a sleeve or a collar to orient the shirt, but for a robot, every unique wrinkle pattern is a new problem. Most robots are trained using images where clothing is laid flat and all features are clearly visible. As David Held, a robotics researcher at Carnegie Mellon University, explains, the real challenge is not the fabric itself, but the endless variations created by wrinkles and the wide range of clothing types found in the real world. Humans have an advantage because we rely on multiple senses. When we manipulate objects in three dimensions, our eyes and hands together give us rich spatial information. Simply by looking at a piece of fabric, we can intuit its weight, elasticity, and the best way to fold it. We know instinctively that denim will not behave like silk. Robots do not have this intuition. They cannot directly estimate that folding jeans requires more force than folding a light shirt. They must physically interact with the object first in order to plan their actions. Another limitation is the robot hand itself. Human hands are extremely flexible, while many robotic grippers are designed for very specific tasks. A robot that tightens bolts on a car panel may have a gripper built to hold bolts of one exact size. Laundry is different because the shape and size of fabric change every time it is handled. The gripper must adapt precisely to any form the cloth takes. Annika Krajic, a computer scientist at the Keith Royal Institute of Technology and co-author of a 2025 review on robotic folding, points out that handling fabric requires both advanced manipulation skills and high-level reasoning. To teach robots about clothing, researchers often rely on computer vision training systems to recognize visual features of garments. Sometimes they also use physics-based models that treat fabric as a set of masses connected by springs in order to simulate elasticity. Even these models, however, fail to capture the full complexity of real clothing. To reduce this gap between simulation and reality, known as the reality gap, researchers are building better data sets. One example is the ClothesNet project, which includes 4,400 simulated three-dimensional garments with labeled features such as sleeves and collars, giving robots more realistic training material. Once a robot has learned fabric properties, many systems use a strategy called pick and place. The robot identifies a point on the garment, such as the left sleeve, picks it up, and places it at a target location, such as the right sleeve. In these systems, the start point, end point, and motion path are planned in advance based on assumed fabric properties like weight and elasticity. While this sounds straightforward, it makes robots inflexible. If the cloth is heavier than expected or gets caught on a button, the system cannot adjust its motion in real time, and the fold fails to measure performance. Researchers often use a metric called intersection over union, or IOU, which reflects how well the folded layers overlap. A perfect fold has an IOU of 1, meaning the fabric aligns exactly. A 2024 study showed that when folding a rectangular piece of cloth in half, traditional pick-and-place systems achieved an IOU of only 0.41. New approaches aim to give robots the ability to adapt as conditions change. One such method is called Adafold, short for adaptive folding. Unlike traditional techniques, Adafold continuously monitors the fabric during the folding process and adjusts its actions on the fly. It responds to changes in shape and elasticity and corrects its movements to maximize overlap by the end of the fold. In a 2024 study, Adafold achieved an IOU of 0.83, a significant improvement according to Alberto Longini, one of Adafold's co-creators. This kind of dynamic adaptability could help robots function more effectively in a constantly changing world. She is set to begin postdoctoral research at Stanford University. Still, she notes that folding laundry remains a complex problem for robots. Until roboticists fully solve it, everyday chores like laundry are unlikely to be handed over to a real-life Rosie anytime soon. If you would like to hear more explanations like this, subscribing is always appreciated and discussion is welcome.